So yeah, welcome back everybody to PDE Math 365. And today's a little bit more of a theory day, and then maybe tomorrow will be more concrete examples. But like what I want to do is kind of close off the conversation of the wave equation. And so we're going to show that solutions to the wave equation with a forcing function and with initial conditions exist and are uniquely determined. And we're going to use what is commonly called Duhamel's principle in order to do this. And so this is something that, you know, in some sense, it's a theorem, it's a formula, we can write it down, we can test it, but there are different perspectives that you can have on this. And some perspectives are like very powerful and very general. So this method, generally speaking, allows you to pass from a solution to the homogeneous equation with no forcing function and then arrive at a solution to an equation with a forcing function. So it works pretty much for any linear equation. Certainly like linear constant coefficient equation. And so this is a souped up version of the method of variation of parameters from ODE, if you remember that. That's something I really hated in ODE. I still hate teaching it. In that class, it seems to be sort of narrowly constructed to only work with like a few types of functions, but there's a cool video I posted online if you want to go back and look at it. It's Professor Strang is kind of explaining this method and arriving at the end, like to a perspective on it that is kind of the correct perspective, where it's not just this huge formula, but it's really what we call a convolution with a fundamental solution. And we'll try to talk about that today too. But that's enough bird's eye view. Let's try to get into it. So in order to start the discussion, I need to introduce a new concept that applies to the wave equation. So in connection with this Huygens principle, I can introduce something in the xt plane that we call the domain of dependence for a point. So suppose you've got a solution to the wave equation. And I've drawn now the domain of the wave equation. And here's some fixed points. And I'm going to define something that we call the domain of dependence of the point Tx. So you know that for the wave equation, information or initial conditions can only travel at a certain speed. So what this concept is sort of talking about is if you want to look at u of Tx, right? If you want to look at like the amplitude of the wave equation at this point in space-time, which portion of the initial condition could have contributed to that amplitude, right? So if you've got some initial condition down here, this is the wave equation on the infinite string. If you've got some initial condition down here, some initial velocity or whatever, but it's so far that it could not have propagated to that point, then it cannot affect the solution at that point. So the solution to the wave equation can only depend on information that had the possibility to get to that point in the first place. And so you can, based on that description, you could probably define what this is yourself. The idea is you look at these characteristic lines. You look at like x plus, like starting here at x minus ct and going up here at x plus ct. So just consider the those characteristic lines emanating from these 2 points. So this is the line with the positive slope starting from x minus ct, similarly. And then the triangle that you then construct together with its boundary, that's called the domain of dependence of the point tx. So it's a fixed point that creates that triangular domain for you. And so for your first class exercise, sure, it's written in the book, but let's make it a class exercise because maybe you're not looking at the book right now. So I want to write down like a formula for the domain of dependence. So it's going to be all points S x prime inside r plus times r. So all coordinate pairs where, you know, this time direction is positive and space could be anything. A t and x are fixed, so new coordinates s and t that vary around and make up this triangle. This triangle is all points s x prime, s x prime. It's a D, but written in calligraphy script. And we're saying what? S can go from 0 to t. And then what's the range of t? So that's your class exercise. So this is like a multivariable calculus exercise, right? If you wanted to integrate over this domain, then what would you write down to make the other part of the iterated integral? So you're looking for formulas for these vertical lines. So take a minute. So after having given you some time to think and process, so what are the bounds on x prime? So you're really just looking for like formulas for these two lines, which you can write down and then pick up, you know, the two numbers for the bounds. One way to think of it, so when s is equal to 0, so you're certainly starting with x minus ct to x plus ct. And then what are you doing? So you're adding, like, you know, s is not 0, what gets added? So I can add cs to like travel along this line. And I can subtract cs to travel along the other line. So this is like x minus c times t minus x, tt minus s. And this is like x plus c t minus s. Right. So that gives us the domain of dependence of the point x. And so now, why do I bring that up? I want to look at a solution to the following problem. So I want to first consider the wave equation with initial conditions equal to 0. I want to look at utt minus c squared uxx equals some forcing function given by tx. Eventually, I want to solve the more general problem where I specify initial conditions and also specify the forcing function. And right now, I'm looking at the entire line, uh, and so I guess eventually I want to look at fixed endpoints and with these initial conditions not being zero. But for the moment, I want to look at the entire real line, the initial conditions equal 0, and look at this problem with now a forcing function introduced. And the theorem basically says the following, which is that if the forcing function is C1, so if both partial derivatives exist and are continuous, then the solution to that initial value problem is this formula. So do the following integral do the following area integral. So look at the integral over the domain of dependence of the forcing function. It's like an area integral. If you want to write this down as an iterated integral, then you just use those bounds. So let's talk about what this means physically a little bit. And so, yeah, like in some sense, the proof of this is just calculate, take two derivatives, whatever. But then taking the derivatives, like there's a little bit of nuance. But we should also try to understand what the heck is going on here, like why does this work? So the first physical principle that I want to point out is totally makes sense that you're integrating over the domain of dependence. At least certainly anything outside the domain couldn't be involved in determining the value of u tx. The second thing is, like, this formula holds good when the initial conditions are 0. Remember, that's part of this. It's not a general formula. So in fact, if the forcing function is 0 and the initial condition is 0, then your solution is the 0 function, and that is given to you by that equation, so that's good. And so finally, the third thing that I'll kind of remark is, look, like if you've got a string and the only action that's acting on it is this external applied force, then at least to my mind as not a physicist, it kind of makes sense due to like conservation of energy that you might sum up or integrate up all the force that's acting on these time slices, right? So the force can change for any particular fixed time that you're on, and you're kind of like, integrals are really infinite sums, aren't they? So you're kind of like adding up all the force, and that total force is giving you then the displacement up to a constant of the string, like at that point. So that kind of makes sense to me. I don't mind that. And so how do you prove? So how do you prove this? And so this is where Duhamel's principle comes in. And the basic idea, and this is a little bit of a complex idea, is that you want to find a way to reframe this problem in terms of something being equal to 0, but with a non-zero initial condition. Because that's the problem that you already know how to solve. Of course, you're not going to be able to directly write the forcing function as an initial condition because this is two variables. Doesn't really work as a one variable initial condition, but let's see how to get around that. So the first thing that you want to do is you introduce or define this function eta sub s of tx to to be what? So you take some s bigger than 0. And now solve the wave equation starting from s and moving forward. So this is going to solve the wave equation. So put a to s to solve L of a to s equals 0 with initial condition a to s of s x equals 0. This now is the initial condition because you're issuing from s. And the other initial condition, I don't really like this notation because this looks like it should be a partial derivative, but it isn't. It's s, it's this parameter that you're starting from. And the other initial condition that if you take the partial with respect to t and evaluate at t equals 0, then you should get or evaluate at t equals s, because you're starting from s, then you should get the forcing function, but at s. So I'll review that on the picture. So you're starting from the red line and continuing out. Your initial condition is 0 on the red line. And your initial velocity in time is given to you by the forcing function, but restricted to the red line, which is now like this function of x only. Okay. And so you can actually write down a formula for this. You can use D'Alembert's solution to find a formula for this, and you're just translating the origin. So you're translating this line to the right by s units. So that's like t gets replaced with t minus s in D'Alembert's formula. And when you write that down, I'll just copy it down here. Then eta of s has this form. Which makes perfect sense, right? Because in D'Alembert's formula, you get a term depending on the initial condition, g, which is equal to 0, and then an integral term where you're integrating the right-hand side of the ddt, initial velocity. And indeed, you're integrating this with respect to the spatial variable s is fixed in this. It's x minus ct, x plus ct, but you're translating over by s units to start at this point. Okay. And so now it's enough to show that utx is going to be, well, if we want it to be the integral over that domain, we've already got part of it here. And what we're missing is just integrating from 0 to t, right? So then utx is going to be nothing but, this is the claim, that utx is going to be equal to the integral from 0 to t of eta of s t x ds. So if you directly substitute this into that, then you see the integrated integral ds dx prime, which gives you integration over that domain as we discussed. But we like to write it in this form because of what this physically represents. And do note the variable of integration is with respect to this parameter here. So on the one hand, like integrating over this domain of the forcing function is sort of like you're collecting the total force and putting it to create the amplitude. So physically, what is this integral? Well, you're now letting s range from 0 to t. And this function is the amplitude of that wave equation at this point with initial condition given by, velocity given by f of s, like f of sx equals to, or ddt eta of s equals to f of sx. So you've got one wave equation per red line. Each wave equation you record the amplitude at that point, and then you add all those amplitudes up by integration, and that gives you the total amplitude. So you can kind of get this point by integrating the force over the entire domain. Total force gives you amplitude, or you can kind of integrate the amplitude at this point, but now you're integrating over all the solutions that had as their initial velocity the forcing function restricted to that line. So it's two sides to the same coin. And I suspect, I didn't look it up, but I suspect that this was Duhamel's insight, that you could probably, make that integral, and that would give you the result. Okay, so for right now, we really want to just assert that this solves the equation. So we should just check the initial condition and take a couple derivatives, and then we're finished. So let's check. So certainly, let's try to be better about keeping my variables in the right order. So this should be like t, this should be 0x. Trying to put the t variable first here. So we want to check that u0x is equal to 0, and certainly that's true immediately. There's no problem there. Integrating from 0 to 0 is equal to 0. Now to check that the initial velocity is also equal to 0, we have to take this derivative. So I need to calculate partial with respect to t of this integral. I'll start this off as a class exercise, or at least I'll give you some time to think about it before rushing in. So it's important to note that this function inside the parentheses, or inside the brackets, it's a function with 3 variables, right? S is a dummy variable, but the 3 real variables are t, and then another slot here, and another one here. And x you're treating like a constant in this situation. So if you want to think of this function as like some function f with variables like x1, x2, x3, then what would the chain rule tell you? That partial with respect to t of, or like derivative I guess it's really derivative with respect to t of this function is going to be equal to. So what is like the chain will tell you? Right. So in particular, I should expect two terms in the sum because for the third term, partial with respect to x times dx dt, definitely going to be 0, x and t being independent. So here I'm thinking I can hold t and x fixed, and I take the derivative with respect to this variable. And so this, it really is now the fundamental theorem of calculus, which says that the derivative of an integral gives you the integrand, but with this plugged in there. So this is like eta of t x plus now the integral from 0 to t of the partial with respect to t of this function. And again, it's kind of awkward because we usually like subscripts for partials, but can't really do that here. So that's the derivative. And I'll take advice from the class. Can you immediately tell me what's that first term equal to just from our definitions? So checking whether we know the definitions. It's a little simpler than that because I think the important thing is that this solves the wave equation starting from like this point and with initial condition that the amplitude at this point is 0. So by definition, this is 0. And then, like, what about this term? Well, remember, this is just the derivative with respect to t. When we then plug in t equals 0, that's what is giving us our initial condition. And so when you plug in t equals 0 to this, of course, you're just integrating from 0 to 0, and you get 0, no problem. So that verifies those initial conditions are correct. And now we have to show that uxt, written down here and written down here, solves this equation. So we already have one time derivative written down there. I want to take another time derivative and show that the answer is equal to c squared uxx plus f. So let's do that now. So let us take a second derivative. So this was u sub t, and second derivative is now the derivative of this with respect to t. And actually, it's the same process as before, but now with a different integrand. So let me give you 45 seconds and have you write that down on your paper. Then I'll show my work and we can compare. Having given you at least some time, so I'll note once again we've got two variables. The first term, by fundamental theorem of calculus, you're going to get this integrand, but now with s substituted in for t, so you're going to get d dt, eta of s tx, but then at the point s equals t, I could have just written down eta of t of x, but then you might get confused and think I'm trying to differentiate that two variable function. I'm not trying to do that. This is like already the derivative of this function with respect to t, and then t is being plugged in for s. So that's important. And then I get the other term, which is now just another derivative. And now this term I can work with because eta of s already solves the wave equation. So this term is definitely equal to c squared times ddx squared eta s. So I'll make that substitution, which is going to be quite helpful. And now, but I'll ask the class or give you an opportunity. Do you recognize this term as some part of the equation based on the definition of eta of s? Yeah, that's right. It's the forcing term because the definition of eta of s was written right here. And so our force restricted to the line, t equals s is what that is. So we get f of s x plus, this now is equal to c squared times, c squared times d dx squared eta of s t x. And I forgot a little bit of notation there, of course. So this would have been differentiation with respect to the second variable. So differentiation under the integral sign. Apologize for that. Just a little typo. But that's great. And so now I think that we are finished. And so why are we finished? So why is this term equal to c squared times uxx? Yeah, that's right. So the way this proof is working is we made a definition of u, and then we're showing that it satisfies the equation. And so long as you believe this theorem from analysis that you can differentiate under the integral sign, that the integral c squared, ddx equals ddx integral c squared times integrand, then you can see that, sort of continue over here to make the conclusion, that then you can see that this is now equal to f s x plus c squared u xx. And since this was reevaluated at t equals s, I can really more properly put t there instead of s. So this function like really solves the wave equation, and certainly the proof is important in that proofs are important, and in showing us some reminders of maybe vector calculus and taking partial derivatives. But even more important, I think, is the two perspectives. So like why these two representations of the solution might give you the answer. In fact, I want to give you even a bit more perspective and bring you back to what I think of and what many people think of as Duhamel's principle. So I want to relate all of this to the idea of convolution. But before I do, are there any questions about what we've just done? Okay. So let me give you this little definition. So let's say f and g are functions, certainly integrable functions, like from R2 to R. So think of them as functions on this xt plane. And then I want to define, you may have seen this before in physics or engineering class, I want to define the convolution of the two functions thusly. So I want to integrate over R2. So I mean, you have to start with functions that are already integrable over the entire plane, or you can't do this. So I want to look at the integral over R2 of, let's say, f of s x prime, and then tx is like the point I'm evaluating at, s x prime are the variables of integration. So I want to take t minus x and x minus x prime. So this function multiplied by the other one, but shifted over by the same parameters. And this definition is completely general. You can do it in any dimension. Just add more subtractions. Why do I care about that? This formula for U is a convolution formula, and I want to explain how that works. And we'll have like more details about convolution at a later time in the course. We'll learn all about its properties and so on and so forth, and learn more about what kinds of functions we're convolving with what and so on. But that's the definition, and that will always be the definition. And so I want to define a function g, I'll call it GTX. This has a name. It's called the fundamental solution of the wave equation, and so it's equal to, it's a step function. It's equal to 1 over 2c in the case that absolute value of x is less than c times t, with t bigger than 0, and it's equal to 0 elsewise. So if I were to draw a picture of the region where this is 1 over 2c, maybe on this plane, what do I get? So this is like x equals, well, let me just draw it with c equals 1. So I can do like x equals ct here. And where is x less than t? It's like all of this stuff, right? So it kind of looks like that region. You're equal to the number 1, does it equal to the number 1 over 2c on that region, and then you are 0 everywhere else. So why is this called the fundamental solution to the wave equation? It has to do with what engineers call impulse response. So the idea is, take your string, or maybe take your sorry, we're doing infinite strings. So here's your x-axis, here's x equals 0. And try to solve the wave equation with the initial condition that the string starts out at rest, but then you're going to put like just a hammer at x equals 0 with infinite force just at that one instant. And then you're going to let the string go. And you can't actually do that, but this is like an idealized situation of just a physical impulse, right? And what this is telling you is that actually, if you do this infinite force here, then as time goes on, you're going to immediately jump to 1 over 2c, and just as time goes on, you're just going to become a constant function. The string lifts up and stays lifted up at the amplitude of 1 over 2c, and then it just continues to travel with that amplitude and stay, as time goes out. So you can't travel faster than the speed c, but because of that infinite force, it kind of perpetuates that amplitude kind of like staying there. There is, of course, no function that is equal to infinity at x equals 0 and 0 everywhere else. Later on in the course, we'll talk about distributions, which is the appropriate way to mathematically contextualize that situation. Certainly, we can understand it now to like what I'm saying. And what I kind of want to claim to you is that if you look at the problem we were just looking at with u 0 x equals u t 0 x equals 0, and with LU equals forcing function f, L being the wave equation like I wrote down before, then the solution, we've already written down a solution for the formula, a formula for the solution. That was the whole point of class. That's fine, but another way to write this is simply take f and take the convolution with g, and you're done. So in some sense, I feel really bad for people learning PDE for the first time, because you have this like big formula and things you got to figure out and whatever. But once you have some perspective, you know that's Duhamel's principle. Just take the convolution with the forcing functions, no problem. And so I want to just kind of show you that this is true, right? And it only takes like 2 or 3 lines, because this is convolution evaluated at the point tx. There's the definition right there. And so the proof, I can just write down the solution uxt, I know is 1 over 2c, integrating over this domain of dependence, f s x prime. And if I write down what that is exactly, remember this is 1 over 2c, integrate from 0 to t, integrate from x minus c, t minus x. Remember way back when we agreed this was the domain of integration for the iterated integral. I was kind of preparing for this moment. And I claim to you that this is it. This really is G. So I should have written this as G star F. You'll learn later on that convolution is symmetric. These two things are the same. It's more convenient for me to write G star F. So plugging into that definition, I'll take G of T minus S, X minus X prime, and then F of S, X prime. Running out of space there on the board, apologize. And so the claim is that these two things are equal. Plus. Yeah, thank you. Thank you. And so what I need to do is to show you that these two things are equal, because that's certainly the convolution G star F. And remember, so the constant 1/2c is built into this function, that's fine. And you're just wanting to say that the domain where this function is equal to 1, times 1/2c is equal to the same set of points where you've got these bounds. And then you're finished. But if you just look at the definition here and kind of plug in, so x is less than ct gives us what? It gives us like x minus x prime in absolute value has to be less than c times t minus s. And here s goes from 0 to t, so that's good. So this inequality makes sense. So you rewrite that as minus c t minus s is less than x minus x prime is less than c t minus s. And I think you kind of want to put x prime in the middle there. So why not just rewrite this inequality as x prime minus x instead of the other way around? Doesn't change anything. And then just add x to both sides and you're done. Because you've got exactly these bounds of integration. And you've got s ranging from 0 to t. So it's kind of amazing, I think, that the fundamental solution or the solution designed to respond to the impulse response, you can either perceive that as integrating forcing function over the domain of dependence. You can perceive that as integrating all these amplitudes for wave equations with initial values. Or finally, you can do this really slick thing of perceiving it as nothing but the convolution with the fundamental solution. And that brings us to the idea that we should try to learn what are the fundamental solutions to all these equations. We should learn a little bit about these setups where you have a distribution or a singular initial condition. So once we keep track of those, we can solve lots more general problems. So I think I'll stop there today and then give you some examples on Friday. But that's the story for how to solve the wave equation with a forcing function. Okay, so thanks everyone.